generally applied to something that conveys information. Signals may, for example, convey information about the state or behavior of a physical system. As another class of examples, signals are synthesized for the purpose of communicating information between humans or between humans and machines. Although signals can be represented in many ways, in all cases, the information is contained in some pattern of variations. Signals are represented mathematically as functions of one or more independent variables. For example, a speech signal is represented mathematically as a function of time, and a photographic image is represented as a brightness function of two spatial variables. A common convention, and one that usually will be followed in this book, is to refer to the independent variable of the mathematical representation of a signal as time, although in specific examples, the independent variable may not in fact correspond to time. The independent variable in the mathematical representation of a signal may be either continuous or discrete. Continuous time signals are defined along a continuum of time and are thus represented by a continuous independent variable. Continuous time signals are often referred to as analog signals. Discrete time signals are defined at discrete times, and thus, the independent variable has discrete values, that is, discrete time signals are represented as sequences of numbers. Signals such as speech or images may have either a continuous or a discrete variable representation, and if certain conditions hold, these representations are entirely equivalent. Besides the independent variables being either continuous or discrete, the signal amplitude may be either continuous or discrete. Digital signals are those for which both time and amplitude are discrete. Signal processing systems may be classified along the same lines as signals. That is, continuous time systems are systems for which both the input and the output are continuous time signals, and discrete time systems are those for which both the input and the output are discrete time signals. Similarly, a digital system is a system for which both the input and the output are digital signals. Digital signal processing, then, deals with the transformation of signals that are discrete in both amplitude and time. The principal focus of this book is on discrete time rather than digital signals and systems. However, the theory of discrete time signals and systems is also exceedingly useful for digital signals and systems, particularly if the signal amplitudes are finely quantized. The effects of signal amplitude quantization are considered in sections 4.8, 6.8-6.10, and 9.7. In this chapter, we present the basic definitions, establish notation, and develop and review the basic concepts associated with discrete time signals and systems. The presentation of this material assumes that the reader has had previous exposure to some of this material, perhaps with a different emphasis and notation. Thus, this chapter is primarily intended to provide a common foundation for material covered in later chapters. In section 2.1, we discuss the representation of discrete time signals as sequences, and describe the basic sequences such as the unit impulse, the unit step, and complex exponential, which play a central role in characterizing discrete time systems and form building blocks for more general sequences. In section 2.2, the representation, basic properties, and simple examples of discrete time systems are presented. Sections 2.3 and 2.4 focus on the important class of linear time invariant, LTI, systems and their time Domain representation through the convolution sum, with section 2.5 considering the specific class of LTI systems represented by linear, constant coefficient difference equations. Section 2.6 develops the frequency domain representation of discrete time SYS. TEMS through the concept of complex exponentials as eigenfunctions, and sections 2.7, 2.8, and 2.9 develop and explore the Fourier transform representation of discrete time signals as a linear combination of complex exponentials. Section 2.10 provides a brief introduction to discrete time random signals. 2.1 Discrete time signals. Discrete time signals are represented mathematically as sequences of numbers. A sequence of numbers x, in which the nth number in the sequence is denoted xnl is formally written as underscore x equals xn, dash 00, where n is an integer. In a practical setting, such sequences can often arise from periodic xa, t. In that case, the numeric value sampling of an analog, i.e., continuous time, signal of the nth number in the sequence is equal to the value of the analog signal, xa, r, at time nt, i.e., xn equals xa, nt, dash 00. 2.2. The quantity t is the sampling period, and its reciprocal is the sampling frequency. Al. Though sequences do not always arise from sampling a log waveforms, it is convenient. 1. Note that we use 1 to enclose the independent variahi of discrete variable functions, and we use to enclose the independent variable of continuous variable functions. Rf. E. 2. T section 2.1 Discrete time signals 1. To refer to xn as the nth sample of the sequence. Also, although, strictly speaking, xn denotes the nth number in the sequence, the notation of EQ 2.1 is often unnecessarily cumbersome, and it is convenient and unambiguous to refer to the sequence xn when we mean the entire sequence, just as we referred to the analog signals t. We depict discrete time signals, i.e., sequences, graphically, as shown in figure 2.1. Al. Though the abscissa is drawn as a continuous line, it is important to recognize that xn is defined only for integer values of n. It is not correct to think of xn as being 0. When n is not an integer, xnj is simply undefined for non-integer values of n. xj x0, x-2 x1 xn, x2. Figure 2. Graphic representation of a n discrete time signal. As an example of a sequence obtained by sampling, figure 2.2, a, shows a segment of a speech signal corresponding to acoustic pressure variation as a function of time. And figure 2.2, b, presents a sequence of samples of the speech signal. Although the original speech signal is defined at all values of time t, the sequence contains information about the signal only at discrete instants. The sampling theorem, discussed in chapter 4. Dash 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 32 ms dash 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 a 1 b. Figure 2.2 a, segment of a continuous time speech signal xa, t. b, sequence of samples xn xa, and t, obtained from the signal in part, a, with t equals 125 j.ls. 12 Chapter 2 Discrete Time Signals and Systems guarantees that the original signal can be reconstructed as accurately as desired from a corresponding sequence of samples if the samples are taken frequently enough. In discussing the theory of discrete time signals and systems, several basic sequences are of particular importance. These sequences are shown in Figure 2.3 and will be discussed next. The unit sample sequence, Figure 2.3a, is defined as the sequence 8n equals, I equals, 2.3. The unit sample sequence plays the same role for discrete time signals and systems that the unit impulse function, Dirac delta function, does for continuous time signals and systems. For convenience, we often refer to the unit sample sequence as a discrete time impulse or simply as an impulse. It is important to note that a discrete time impulse does not suffer from the mathematic complications of the continuous time impulse. Its definition in EQ 2.3 is simple and precise. 1 unit sample ON A unit step 1 ON B real exponential ON C sinusoidal J11 TTLI 303 and Figure 2.3 Some basic sequences. The sequences shown play important roles in the analysis and representation of discrete time signals and systems. Section 2.1 Discrete time signals 13. PN 8n Figure 2.4 Example of a sequence to be represented as a sum of scaled delayed impulses. One of the important aspects of the impulse sequence is that an arbitrary sequence can be represented as a sum of scaled, delayed impulses. For example, the sequence Pn in Figure 2.4 can be expressed as Pn equals a underscore 30n plus 3 plus a 18n, 1 plus a 28n, 2 plus a 78n, 7. 2.4. More generally, any sequence can be expressed as 0 0 xn equals lxkon, k. 2.5. K equals 00. We will make specific use of EQ 2.5 in discussing the representation of discrete time linear systems. The unit step sequence, Figure 2.3b, is defined as 1 and 2, 0. Un equals 0, degree, 2.6. n. The unit step is related to the unit impulse by n. Un equals L8k, 2.7. K equals 00. That is, the value of the unit step sequence at time index n is equal to the accumulated sum of the value at index n and all previous values of the impulse sequence. An alternative representation of the unit step in terms of the impulse is obtained by interpreting the unit step in Figure 2.3 b in terms of a sum of delayed impulses, as in EQ 2.5. In this case, the non-zero values are all unity, so Un equals 8n plus 8n, 1 plus 8n, 2 plus 2.8a. Or 0 0. Un equals L8n, k. 2.8b. K equals 0. As yet another alternative, the impulse sequence can be expressed as the first backward difference of the unit step sequence, i.e. 8n equals un minus 1. 2.9. Exponential sequences are another important class of basic signals. The general form of an exponential sequence is 2.10. If a and a are real numbers, then the sequence is real. If 0, then the sequence values are positive and decrease with increasing n, as in figure 2.3, c. 14 Chapter 2 Discrete Time Signals and Systems. For -1. With increasing n. If lal1, then the sequence grows in magnitude as n increases. The exponential sequence an with a complex has real and imaginary parts that are exponentially weighted sinusoids. Specifically, if a lal wqna equals ia the sequence an can be expressed in any of the following ways. xn equals an equals ia pln jwqfl ia ilfla 1h 2.11 equals ia encos 1 plus. The sequence oscillates with an exponentially growing envelope if lal or with an exponentially decaying envelope if lal. As a simple example, consider the case wo rr. When lal equals 1, the sequence has the form JOH 2.12. xn equals IALE, WLL, IA ICOS, 1 plus. That is, the real and imaginary parts of each whole vary sinusoidally with n. By analogy with the continuous time case, the quantity wo is called the frequency of the complex sinusoid, or complex exponential, and is called the phase. However, since n is a dimensionless integer, the dimension of wo is radians. If we wish to maintain a closer analogy with the continuous time case, we can specify the units of wo to be radians per sample and the units of n to be samples. The fact that n is always an integer in EQ 2.12 leads to some important differences between the properties of discrete time and continuous time complex exponential sequences and sinusoidal sequences. Consider, for example, a frequency, wo plus 2rr. In this case, xnl equals ae, wo plus 2rr, 1l. 2.13 equals alveola 2rr and aejwo flow. Generally, complex exponential sequences with frequencies, wo plus 2rr, where r is an integer, are indistinguishable from one another. An identical statement holds for sinusoidal sequences. Specifically, it is easily verified that xn a cos, wo plus 2rr, n plus 2.14 a cos, 1 plus. The implications of this property for sequences obtained by sampling sinusoids and other signals will be discussed in Chapter 4. For now, we conclude that, when discussing complex exponential signals of the form xn equals a whole or real sinusoidal signals of the form xn a cos, 1 plus 2rr, typically, we will choose either rr. Another important difference between continuous time and discrete time complex exponentials and sinusoids concerns their periodicity in n. In the continuous time case, a sinusoidal signal and a complex exponential signal are both periodic in time with the period equal to 2rr divided by the frequency. In the discrete time case, a periodic sequence is a sequence for which xn plus n, for all n, 2.15. p. Section 2.1 Discrete Time Signals 15. Where the period n is necessarily an integer. If this condition for periodicity is tested for the discrete time sinusoid, then a cos, 1 plus cp, a cos, 1 plus cp, 2.16. Which requires that 1 equals 2 rck, 2.17. Where k is an integer. A similar statement holds for the complex exponential sequence. Stwo flow, that is, periodicity with period n requires that 2.18. Which is true only for 1 2RCK, as in EQ. 2.17. Consequently, complex exponential and sinusoidal sequences are not necessarily periodic in n with period, 2RC/wo, and, depending on the value of wo, may not be periodic at all. Example 2.1 Periodic and aperiodic discrete time sinusoids. Consider the signal xln equals cos 7 in/4. 111 is signal has a period of n equals 8. To show this, note that xn plus 8 equals cos rc n plus 8/4 cos rc n/4 plus 2 rc equals cos 7 in/4 x New Jersey, satisfying the definition of a discrete time periodic signal contrary to continuous time sinusoids. Increasing the value of VO for a discrete time sinusoid does not necessarily decrease the period of the signal. Consider the discrete time sinusoid x2n1 equals cos 3nn/8, which has a higher frequency than xln. However, x2n is not periodic with period 8, since x2n plus 8 cos 37i n plus 8/8 cos 37 in/8 plus 3n x2 New Jersey. Using an argument analogous to the one for xln, we can show that x2n has a period of n equals 16. Thus, increasing the value of VO equals 27i/8 to VO 3n/8 also increases the period of the signal. This occurs because discrete time signals are defined only for integer indices n. The integer restriction on n results in some sinusoidal signals not being periodic at all. For example, there is no integer n such that the signal x3n equals cos n satisfies the condition x3n plus n equals x3n for all n. These and other properties of discrete time sinusoids that run counter to their continuous time counterparts are caused by the limitation of the time index n to integers for discrete time signals and systems. When we combine the condition of EQ 2.17 with our previous observation that wo and wo plus 2n are indistinguishable frequencies, it becomes clear that there are n distinguishable frequencies for which the corresponding sequences are periodic with period n. One set of frequencies is wk2 and k/n, k equals 0, 1, n, 1. These properties of complex exponential and sinusoidal sequences are basic to both the theory and the design of computational algorithms for discrete time Fourier analysis, and they will be discussed in more detail in chapters 8 and 9. Related to the preceding discussion is the fact that the interpretation of high and low frequencies is somewhat different for continuous time and discrete time sinusoidal and complex exponential signals. For a continuous time sinusoidal signal SU equals 2 cos cot plus Cp, as Qo increases, xt oscillates progressively more rapidly. For the discrete time sinusoidal signal xn equals a cos 1 plus Cp, as wo increases from wo equals 0 to ward wo equals Rc, xn oscillates progressively more rapidly. However, as wo increases from wo rr to wo equals 2n, the oscillations become slower. This is illustrated in figure 2.5. In LD2 ON A wo equals n/8 or wo equals 15n/8 N B wo equals nl4 or wo equals 7nl4 ON C wo equals n ON D Figure 2.5 cos 1 for several different values of WO. As W0 increases from 0 toward n, parts AD, the sequence oscillates more rapidly. As WO increases from n to 2n, parts dA, the oscillations become slower. 16. Section 2,2 Discrete Time Systems 11. Fact, because of the periodicity in WO of sinusoidal and complex exponential sequences. WO equals 2RR is indistinguishable from WA equals 0, and, more generally, frequencies around WA equals 2RR are indistinguishable from frequencies around WA equals O. As a consequence, for sinusoidal and complex exponential signals, values of WO in the vicinity of WO equals 2RRK. For any integer value of k are typically referred to as low frequencies, relatively slow oscillations, whereas values of WO in the vicinity of WO equals RR plus 2RRK, for any integer value of k are typically referred to as high frequencies, relatively rapid oscillations.